Hello everyone, this is Zhao Zhang. Today we will look at some problems for the homework one. Let's start. For the problem one, we know a mercury manometer is used to measure pressure in the pipe in this figure, and we need to determine the pressure in the pipe in psi and in inches of mercury. And from the problem, we know that h is 3 feet, and we can draw a horizontal line through the lower surface of the manometer. And we assume this is 0.1 and this is 0.2. So the pressure at 0.1 and 2 must be the same since the system is static equilibrium. So we can write the first equation for this problem, that's P1 equals P2. This is first equation. And for the open manometer, the pressure on the 0.1 is exerted by the weight of the mercury column above 0.1. So we can write the second equation for this problem, that P1 equals height of mercury times specific weight of mercury. This is equation 2. And when you know that the specific weight of mercury equals the specific gravity of mercury times the specific weight of water. And for this value is the 30.6. We can find this value online or on the book. And when the problem doesn't provide the temperature of the water, the commonly value used for the specific weight of water is the 62.3 pounds per cubic feet. So now we can write the P1 equals 3 feet times 30.6 times 62.3 pounds per cubic feet. And for the pressure on the tube is exerted by the weight of the water column above 0.2 plus the pressure in the vessel. So we can write the third equation, P2 equals the height of water times specific weight of water plus P. The P is the pressure in the vessel. That's we need to determine this problem. And we know that the height of the water above the 0.2 is 2 feet. And the specific weight of the water is 62.3 pounds per cubic feet. So now we can write that P2. Oh, I forgot. This is equation 3. P2. Now the P2 equals 2 feet times 62.3 pounds per cubic feet plus the P. So according to the equation 1, 2, 3, now we can write that 3 feet times 6 times 62.3 equal pounds per cubic feet equals 2 feet times 62.3 pounds per cubic feet plus P. Now we can get the P equals 2,420 pounds per square feet equals 16.8 psi. From the problem, we also know that the pressure also need to be expressed as the height of the mercury. So the height of mercury now equals P divided by the specific weight of mercury equals 2,420 pounds square feet divided by 13.6 times 62.3 pounds per cubic feet. So equals 2.86 feet equals 34.3 inches. So we have done this problem. For the second problem, we know a circular gate is installed on a vertical wall as shown in this figure. We need to determine the horizontal force P necessary to hold the gate closed. We shouldn't neglect the frictions at the pivot. To determine the horizontal force P, we need to determine the hydrostatic force on the gate firstly and its location. First, we place the x-axis on the line where the surface of water intersections with the wall surface. So this is intersections. So actually the x-axis is into the page. We also place the y-axis running downward along the surface of the wall. So this is y-axis. So according to the hydrostatic force equation, we know that hydrostatic force equals specific weight of water times sine theta times area of the gate times the y bar. Theta is angle between the surface of water and the wall. And we know this is a vertical wall, so the theta is 90 degrees. So that means sine theta equals 1. And the y bar is the distance measured from the x-axis to the centroid of the gate. Since this is a circular gate, that means the centroid of the gate is a pivot. So this is the y bar. So we can see that y bar actually equals h. So now we can write F equals gamma times A times H, because we know the diameter of the gate is D, so we can write as pi times D squared divided by 4. So now F equals gamma times H times pi D squared divided by 4. We write this as equation 1. And then now we also need to determine the location to determine the location of hydrostatic force. So we have equation that yp equals y0 a times y bar plus y bar The y sub p is the distance measured from the x-axis to the center of the pressure. Actually, the yp is the location of F, and the I sub 0 is a moment of inertia of the gate. We can find that in the moment of inertia for the circle is pi times d to the power of 4th divided by 34. And from the previous step, we also know y bar equals h. So we can get that yp equals d squared divided by 30 is 16h plus h. We write this equation 2. Then, because we should hold the gate closed, that means the moment at the pivot should be 0. So the moment at the pivot should be 0. So we also can write this as p times d divided by 2 minus f times yp minus h equal 0. So according to, sorry about that, p times d, and according to equation 1 and equation 2, now we can get that p equals 1 divided by 32 times gamma times pi times d to the power of 3rd. So we have done this question. For the third problem, a horizontal commercial steel pipe 1.5 meter in diameter carries 3.5 cubic meter per second of water at 20 degrees Celsius. We need to calculate the pressure drop in the pipe per kilometer length. Assume that minor losses are negligible. So from the problem, we know that D equals 1.5 meter and its flow rate is 3.5 cubic meter per second, and length equals 1000 meter because per kilometer length. So from the Q and D, we can calculate the velocity. Velocity equals Q divided by pi times d squared divided by 4. So this value is 1.98 meter per second. And then we'll write the energy equation. H1 plus P1 divided by gamma plus V squared to G equals H2 plus P2 divided by gamma plus V1, V2 plus head of loss. Because this is a horizontal pipe, so H1 equals H2. And we know the diameter of this pipe didn't change, though the V1 equals V2. And the minor losses are negligible, so head of loss equals friction loss. Now, the energy equation can be written as P1 minus P2 divided by the gamma equals HF. So if we know the friction loss, we can calculate the pressure drop. So according to the Darcy-Weisbach equation, we know that HF equals F times L divided by D times V squared divided by 2G. We know all of these values, so we just need to determine the friction factor. We need to use Morley diagram to determine the friction factor. So we must solve relative roughness and the Reynolds number. And we know this is a commercial steel pipe, so the roughness height equals 0.045 millimeter, and so we can know the relative roughness equals 0.12343, and the Reynolds number equals D times V divided by the kinematic viscosity. And at the 20 degrees Celsius, the kinematic viscosity is 1 times 10 to the power of -6. So we can get a Reynolds number is 2.96 times 10 to the power of 6. And from the Morley diagram, we can determine F equals 0.011. So now we know, this is equation 1. So we know the friction factor, so we know the friction loss equals point times divided by 1.5 times 1 square divided by 2 times so the hand loss is 1.47 meter. And we also know at the 20 degrees Celsius, the specific weight of water equals 97910 Newton per cubic meter. So we substitute the friction loss and the gamma to the equation 1. So we have that the pressure drop equals 10 times 1.47 meter. So the value is 14.4 kilonewton per square meter. So we finished it. For the fourth problem, we need to determine the flow rate of water that will cause a pressure drop of 70,250 Newton per square meter in 350 meter of horizontal cast iron pipe with a diameter equals 16 centimeter. Ignore the minor losses. So from this problem, we know that the diameter equals 0.6 meter and the pressure drop equals 17,250 Newton per meter, and the length of the pipe equals 350 meter. And then we'll write the energy equation. H1 plus P1 divided by gamma plus the V1 square 2G equals H2 plus P2 divided by gamma plus the V2 square divided by 2G plus the loss of head. And then because this is a horizontal uniform pipe, so H1 equals H2, V1 equals V2. And we ignore the minor losses, so the loss of head just equals the friction head loss. And now the energy equation can be written as P1 minus P2 divided by gamma equals HF. Because we know the P1 minus P2 equals 17,250 Newton per meter, and at the 20 degrees Celsius, the specific weight of water equals 9,790 Newton per cubic meter. So we can calculate that HF equals 1.76 meter. And then we also know the friction head loss also equals F times L divided by D times V squared by 2G. And the Reynolds number equals D times V divided by the kinematic viscosity of the water. So at 20 degrees Celsius, this value equals 1 times 10 to the power of negative 6 meter per second. So this is So this is equation 1. This is the equation 2. Since the velocity is not available on these questions, so Reynolds number can be solved. However, we know this is cast iron pipe, and the diameter is 16 centimeters, so we can calculate the relative roughness equals 0.26 millimeter divided 200 millimeter. So the relative roughness equals 0.00433. And then we use this relative roughness and the MODI diagram to obtain a trial F value by assuming that flow is in the complete turbulence. So we try F equals 0.017 and solve the equation 1. So we get equation 1. So we got 1.676 meter equals 0.17 times 350 meter divided by 0.6 meter times velocity 2 times 9.8. So we can got that velocity equals 1.87 meter per second. Then we use this value. Then we use this velocity value in the equation 2. So we use velocity value in equation 2. We got a random number equals 1.12 times 10 to the power of 6. And then this real number and this relative roughness are taken to the MODI diagram to obtain a new friction factor, and we can find that the new friction factor also equal to the 0.016, which is unchanged from the assumed one. So we need to know that if the friction factor was different, then additional irritations would be performed until the trial F and the computed F are essentially equal. In this question, the assumed the trial F is equal to the computed F, so we can use the velocity to calculate the discharge. So the discharge is calculated as Q equals A times V equals pi divided by 4 times 0.6 meter square times 1.87. So the discharge is 0.529 cubic meter per second. For this problem, water flow through of 4 centimeter wrought iron horizontal pipeline from point A to point B. The pipeline is 15 meters long and contains a fully open gate valve and 2 elbows with R divided by D equals 4. If the pressure at B is 192 kilopar and the flow rate is 0.006 cubic meter per second, we need to determine the pressure at point A. So from this problem, we know the diameter of this pipeline equals 0.804 meter, and the flow rate equals 0.006 cubic meter per second. So we can get that velocity equals q divided by times d squared divided by 4. So this value is 4.77 meter per second. And we know the length of this pipe equals 15 meter. And the pressure at B equals 192 kilopar. And then this pipeline contains a fully open gate valve. So the fully open gate valve, we can get that the coefficient of valve equals 0.15. We can find this value on the table at the textbook. And also this pipe contains 2 elbows. With R divided by D equals 4. So we can get the coefficient of the elbow equals 0.17. And then we write the energy equation. HA times plus PA divided by gamma plus the VA squared divided by 2G equals HB plus PB divided by gamma plus VB squared divided by 2G plus loss of head. Since the pipe is a horizontal uniform pipeline, so we can get HA equals HB, VA equals VB equals VA, and the total loss of hand includes the friction hand loss and the hand loss incurred at the valve and the 2 elbows. So we can write the total loss of head equals F times L divided by D plus EV plus 2K B times V squared divided by 2G. And now the energy equation can write as PA divided by gamma equals PB divided by gamma plus D 2B times V squared divided by 2G. This is equation 1. The value we don't know on the right side of the equation is a friction factor. So we need to find the friction factor. To determine this friction factor, we need to know the Reynolds number. Reynolds number and the relative roughness. Real number equals D times V divided by kinematic viscosity. The problem doesn't tell us the temperature of the water, so we always assume that the water is 20 degrees Celsius. So at 20 degrees Celsius, the kinematic viscosity equals 1 times 10 to the power of -6 square meter per second. And we know the D value and the V, so we can get that Reynolds number equals 1.91 times 10 to the power of 5. And we also know this is round arrow pipeline, so we can get the reference height of the E. So this is the point 0.45 millimeter, and the diameter of this pipe is 40 millimeter. So this value equals 0.00113. And from these two values, and we can use a multi-diagram to find that the friction factor F equals 0.022. And then we can solve equation 1. So the PA divided by 9,090 Newton per cubic meter, because we assume the water temperature of the water is 20 degrees Celsius, so the specific weight of water at the 20 Celsius degree is 9,790 Newton per cubic meter. So this equals PB is 1,000 divided by 990 plus F is 0.022 times the length is 50 meter divided by 0.04 meter plus 0.15 plus 2 times plus 2 times point times 40 meter per second square divided by 2 times 9 meter per square. So we can get that the pressure at point A equals 510 kilopascal. We have done. After reading the question, we know there are 2 strategies in this question. I have jotted them. For the first strategy, we know the pipe with 20 centimeter diameter. So diameter for this pipe equals 0.2 meter. And the length of this pipe is 800 meter. So length equals 800 meter. And for the second strategy, the pipe includes 2 parts. The diameter for this part is 30 centimeter diameter, so the D prime equals 0.3 meter. I use prime to indicate this is for the second strategy. Since engineers are considering replacing 94% of the pipe length with our largest steel pipe and the 30-degree confusion that connects to the remainder of the small pipe. So now we know the length of this part equals 94% times L pi 800 meter. So this is 0 meter 52 meter. 152 meter. And we need to determine the pressure head that would be gained by this strategy. This strategy means the second strategy, this one. So we first write the energy equation for two strategies. So for the first strategy, the energy equation gamma plus V1 squared 2G equals 2 plus P2 squared plus hand loss. So this is equation 1 for the second strategy. H2 plus P2 divided by gamma plus, oh sorry, this also is H1 P1 V1 squared H2 plus P2 pi divided by gamma plus V2 pi square divided by plus H L pi. This is equation 2. So because the pipe at the delivery point didn't change, so the V2 equals the V2 prime. And then we use equation 2 minus equation 1. We will get P2 prime gamma divided minus P2 gamma equals HL minus HL prime. Now, if we can determine the difference between the head loss under the first strategy and the second strategy, we will get the answer. So also for the first strategy, because there is no minor losses, so the head loss equals the friction loss. So we write the Darcy-Weisbach equation. Hf equals F times L by D times V square 2G. This is equation 3. We can calculate the velocity equals Q divided by A. Use Q divided by pi d squared 4. So value, because we know the Q equals 0.1 cubic meter per second, and pi times 2 square divided by 4. So the value is 3.18 meter per second. And we know the V, so we can get the Reynolds number equals D times V times divided by kinematic viscosity. So the value mean times 3 square 1 times 10 to the 6 square meter So this value is 6.35 times 10 to the power of 5. And because we know this is commercial steel pipe, so the relative roughness equals 0.04 millimeter divided by millimeter. So value is 0.00225. Now we know the real number and the relative roughness number. So we can find the friction factor F from the Modi diagram. So we can find that F equals 0.0155. So now we can solve equation 3. So the head loss equals the friction loss equals 0.155 times meter divided by 0.2 meter times times 9.1. So the friction loss is 32 meter. Now for the second strategy. Sorry. For the sorry. For second strategy, the total head loss equals HF 3 plus 3 plus HF. This means the friction loss in the larger pipe. This is the hand loss at the confuser. And this is the friction loss in a small pipe. So we also use the Darcy-Weisbach equation. So the friction equals F times S times V squared by 2G. It's equation 4. Now we can calculate velocity equals Q divided by A by Q divided by pi times D pi square 4. So equals 0.1 cubic meter per second divided by pi times divided by 4. So the value is 1.41 meters square. So now we also can get the real number equals D by lambda times 1.1 divided by 1 times 10 to the negative. So the value is 4.23 times 10 to the power of 5. And the relative roughness equals 0.05 meter divided by 300 millimeter. So this value is 0.0015. The same, we know a real number and roughness. We can find the f from the MODI diagram. So we found f equals 0.01552. Now we can solve equation 4. So friction in the larger pipe is 0.155 times meter 141 meter per second square divided by 91 per second. So the value is 3.94 meter. Next, we will calculate the head loss at the confuser. And we can write the equation that equals the coefficient of confuser times v squared 2g. We need to know this is equation this is equation 5. So we need to know that the velocity is a small pipe velocity. So we have calculated before, so V equals 3.8 meter per second. Now, we also know A divided by A1 equals 0.444. This is cross sector area of small pipe. Small pipe. And this is a cross-sectional area of larger pipe. And then we also know this is a 30 degree confuser. So we can extrapolate the figure 3.11 in the textbook. So we will get that the coefficient of confuser equals 0.025. Then we can solve equation 5. So the head loss at confuser equals 0.2 times 9 square 2 times 981. So the value is 0.0129 meter. Now we need to calculate this value. the friction loss in the small pipe. So 20 equals 6% times HF. This is because the only 6% of the pipe length with the small pipe in the second strategy. And this value we have calculated in the first strategy. This is 32 meter. So we can get the friction loss at the small pipe equals 1.92 meter. Now the total head loss in the second strategy is equals 3.94 meter plus 0.0129 meter plus 1.92 meter. So the value is 5.87 meter. So now we can get the pressure head again. Equals the head loss in the first strategy minus the head loss in the second strategy. So value is there minus meter. So the value is 26.1 meter. Oh, we have done this problem. So for the last problem, we know the diameter for the tank is 16 feet. We know D equals 16 feet. We use the capital D to represent the tank diameter. And this tank contains 10 feet of the water depth. So this H equals 10 feet at the initial stage, because we need to drain the tank, so the water depth will change. And a short horizontal pipe with an 8-inch diameter and a rotary volume. Oh, I think there is a tempo. It should be a rotary valve is used to drain the tank from the bottom. So we know the D, the pipe diameter equals 0.667 feet. So we know the entries is squared H. So the coefficient of the entries equals 0.5. We can find this value in the textbook. And there is a rotary valve. So the coefficient of valve equals 10. And we know the friction losses are negligible. So the friction loss in the pipe equals 0. And for this problem, we need to determine the time to drain 15% of the tank. So now we need to apply the energy equation from the surface of storage tank 1 to the outlet of the pipe 2. So we will get H1 plus P1 divided by gamma plus V1 square to G equals H2 plus P2 gamma plus V2 square plus head loss. We select the reference datum at the outlet. So reference datum. So we got H2 equals 0 and the H1 equals the water depth. And since the surface of the tank and the outlet of the pipe both exposed to the atmospheric pressure, so we get P1 equals P2. And the velocity at the free surface is very low in the tank and it can be neglected. So we will have V1 equals 0. And since we know the friction loss is negligible, so the head loss equals minor losses. So it equals Kc plus Kv times V2 square by 2G. So now the energy equation can be written as H equals V2 square plus Kc plus V times square divided by 2G. We will rearrange this equation. We can get that V2 equals G times H 1 plus Kc plus Kv power of 1 divided by 2 equals times feet per second square times H 1 plus 10 plus 0.5. So the V2 equals 2.37 times H to the power of 1 divided by 2. And now for the tank flow, the Q equals the derivative of the water value in the tank with respect to the time. So write D pi times 4 times H divided by dt. So pi times d4 times dh by dt. So this is equation 1. And for the pipe flow, Q equals the sectional area of pipe times V2 equals pi times d squared divided by 4. Because of V2 we have calculated before, so times 2.73. So from the problem, we need to determine the time to trace 15% of the tank. So we know equation 1. Oh, this is equation 2, sorry. Equation 1 equals equation 2. So we will get that pi 4 times d divided by dt equals pi times d 4 times so we can get that the dt equals dh divided by 2.3712. Yeah, and integrating this equation, we will get that the t equals 1 divided by 2.37 times d squared divided by small d squared, integrate 10 5 to the power dh. Since we need to drain 50% of the tank, so h1 equals 5 feet, so h2 equals 10 feet. So now we can get that dt, the time, equals 1 point times 16 feet square divided by 0.667 feet square times 10 feet minus 5 feet. 5 feet. So we can get that t equals 450 seconds. So we have done.